Before we begin with the normal probability distribution, let's just take a couple of minutes to review. Our study of statistics began with a discussion on types of data. We talked about categorical data and quantitative data. Remember, categorical data are just categories which could be at two different levels, nominal data or ordinal data, and then quantitative data, the numbers that represent counts or measurements, and these were the levels we talked about were interval and ratio, and quantitative data can be discrete or continuous. We also talked about sampling methods, and we said that the most important sampling method for us as we continue with our study of statistics is the simple random sample, but there are other random samples that we discussed and learned about: the systematic samples, stratified samples, and cluster samples. Okay, so we saw many ways to display both that quantitative data and the categorical data in different tables and graphs. And then we learned to calculate some characteristics of the data that are of interest to us. We continued with our quantitative data and said, well, now we can calculate some statistics, and we looked at measures of center, primarily the mean, median, and mode, and measures of variation, primarily the standard deviation and the range, although we did discuss the variance a little bit. And we talked about the distribution of the data, the different shapes that the distribution can take. And in some of our graphs, we saw that we could get a feel for that distribution through the graphs that we were using. So then our transition from descriptive stats to inferential statistics was done with the beginnings of studying probability, and that then led us into our probability distributions. And our last discussions have been about the specific probability distribution called the discrete probability distributions. With the discrete probability distributions, remember that the random variable represents counts. So here, the random variable that we were calling x represents counts. Okay, and now we're moving into the other type of probability distribution we'll study, called the continuous probability distribution. And here the random variable represents a measurement. So therefore, there are infinitely many values for the random variable x, since our data is coming from things that we are measuring. So to illustrate the correspondence, that correspondence between area and probability, the area under the curve and probability, we'll begin with the continuous probability distribution called the uniform distribution. So this continuous probability distributions, there are different ones. We will start with a discussion of the uniform distribution, and that done, we will then focus on the continuous probability distribution known as the normal distribution. The normal distribution often occurs in real-world applications, and they play an important role in inferential statistics. So we'll look at the uniform distribution just to get that feel for that connection of the area under the curve and probability, and then we'll translate that into a very important probability distribution called the normal distribution. Now, the normal distribution has a graph that is symmetric and bell-shaped. So we have, get another color here. So we have this graph of a normal distribution. It's symmetric and bell-shaped. So by being symmetric, what we mean is there's a peak right here in the middle. Not a very straight line, but hopefully you get the idea. and then each side of this at the peak, on either side, these two sides are symmetric, or mirror images of each other. So it is symmetric and bell-shaped. Okay, and this is, let me put a label up here, the normal distribution. It's a continuous probability distribution. And the area under this curve is equal to 1. Likewise, the area represents probability. Therefore, the probability, the sum of all the probabilities under the curve is equal to 1. So area is probability. And so our horizontal axis here are the values of the random variable x. So this is our x on this axis here. And our y-axis, this is our probability. So that the higher we are on the curve, the greater the probability of that value of x. So right here in the middle is our highest probability, and that would be for our mean, mu, because that is the measure of central tendency that says it's the most common value. Right here represents it would have the highest probability of occurring because it's our mean. So again, this is a curve. It has a, just like any graph of a line or a curve has an equation. The equation is much more complicated than the graph of a line. You recall, like y equals mx plus b would be an equation for the graph of a line. The equation for this curve is much more complicated than the equation of a line, and it involves two mathematical constants, pi and e, as well as fixed values for mu and sigma. And that equation may be found in your textbook. We won't be using that specifically to make calculations, but it does involve those different constants and values for mu and x. Okay, so we want to start getting an idea for this curve representing the area under the curve representing the probability, and this is our normal distribution, a symmetric bell-shaped curve.